Hello everyone, welcome to another video of statistical mechanics. We'll be solving more numericals in this session. Okay. And, we had done so many numericals from microcanonical and ensemble, I think, in the previous class. So we'll be solving more questions here. So here we'll be discussing about canonical ensemble in this sorry, canonical ensemble. Okay. This is a special video for JEST. Our JEST exam is coming on March 3rd, so we're preparing for that. So first of all, what is um, what is an ensemble? First of all, what is an ensemble? What is an ensemble? If you see, what is an ensemble? Ensemble is a collection of large number of mental copies of original system that is macroscopically identical, but different microscopically. Different microscopical. Okay. Collection of large number of mental copies of original systems that is macroscopically identical but different microscopically. Okay. First of all, um, see, this is suppose a microstate. Okay, microstate. It's a function of NVT. Right. See, all systems are in thermal equilibrium or are in contact with extra heat reservoir. Okay, heat reservoir which has an infinite heat capacity. So, see, this microstate can be this, can be this, this. What is this? This is the heat reservoir. This is a microstates. So it can have heat exchange, heat, heat or energy exchange. Okay. So there, like how heat is exchanged, whether it is exchanged or not, it depends on the walls. Also, okay. So you can write system walls. What kind of walls are there? We will write. Okay. Whether it is impenetrable wall or rigid walls. Okay. We will see. If your n is constant, okay, if your n is constant, it is called impermeable or impenetrable impenetrable wall. Okay. If your v is constant, it is called rigid walls. If your volume is constant, they are called rigid walls. If your t is constant, this is called diathermic wall or thermally conducting walls. Thermally conducting walls. Thermally conducting, right? Is it all right? Okay. Now, uh, See here, each system in this ensemble is actually exchanging heat with the reservoir. Okay, to attain what? Thermal equilibrium. So before achieving equilibrium, the energy of RH system can be anything between 0 to infinity. Okay, energy of the RH system, we can write it like this. Energy of the RH system can be 0 to infinity. Or you can say RH system can be found out in energy level ER. Okay, because here energy is actually variable in canonical ensemble. Alright. Okay, so let's write a question based on it. Let's write a question based on it. Question number one. What is the probability? What is the probability? What is the probability that RH system will be found out in energy level ER. In energy level. What is the probability that RH system can be found out in energy level ER? Or what's the probability? What is the probability that RH system RH system will have energy ER or okay energy ER. What's the probability that the RH system will be found out in energy level ER? What's the probability that RH system will have energy ER? So this is the question here. Okay, let's do it. Okay, what is probability? We know probability, the original formula, the basic formula of probability is what? Probability is favorable cases divided by total number of cases. Favorable cases divided by total number of cases is the probability. Okay, so uh, we can say P of ER is equal to number of systems in energy level ER divided by total number of systems in all energy levels. In all energy levels. Number of systems in energy level ER divided by total number of systems in all energy levels. So how will we do it? P of ER is equal to how much? Then, it will be GR e to the power minus beta ER divided by summation R GR e to the power minus beta ER. Okay, this is all right. This is the probability. Okay, this is the probability. Now, what is the partition function? This is the probability. What is the partition function? Partition function will be how much? It will be denoted by Q. Q or Z. Okay, Q. So Q is your what? Q is your summation R GR e to the minus beta. The denominator is actually Q or Z. You can write Z. Okay. So what does partition function actually tells us what? That how the various system or members of the ensemble are distributed in various energy levels. Okay. So you can write one point here. Partition function. Partition function tells that how the various system or members of an ensemble are are distributed in various energy levels. Partition function tells that how the various system or members of an ensemble are distributed in various energy levels. Alright, this is your partition function. This is the like basic understanding of partition function. Alright. Mm, Next, let's calculate relation between internal energy U and partition function Q. Okay. What is internal energy exactly? Internal energy U is what? It's actually the mean value of mean of the energy value of that system. U is equal to this, and U is what? U is actually U1, U2, U3, and all. So U mean will be, we can write like this. Okay. We can also write like this. Okay. Any average value I can write like this. So I can write the ER value like this then. ER mean value is equal to summation R. Hmm. ER P of ER. Is it correct? Okay. And now P of ER we know. Here we have written here. This is P of ER. Let's put it there. Let's put it there. So summation R ER. P of ER is how much? GR e to the power minus beta ER whole divided by summation GR e to the power minus beta ER. Okay. So I just put the value of PER from the previous cases. Okay. So here I will just multiply it here. Summation R GR ER e to the power minus beta ER divided by summation GR e to the minus beta. Is it alright? Okay. So if you see, um, okay, if you see this thing is actually, this thing is actually the derivative of, if I can write this as minus del by del beta of ln summation gr e to the minus beta. Okay, I can write like this. So if this is actually partition function, so I can write minus del by del beta of ln q or ln z, anything. Let's write ln z. Z is a partition function. So this is your what? ER, which is equal to u. So I can write u is equal to minus of del by del beta of ln z. Where beta is a what? Beta is a 1 by kbt. When needed, you can put. So let's put 1 by kbt here then. So minus 1 by del of 1 by kbt ln z. Okay, d of 1 by kbt I can write what? That means derivative of this. That means I can write it as minus 1 by kbt square into del t. Right? I hope you understand. This is simple differentiation only. Minus minus cancel out. This kb goes up. T square goes up. So kb t square del by del t of ln z. This is also an expression of average energy or internal energy. Okay. All understood. kVt square del by del T of L in Z. Okay. Now, this is a relation between internal energy and partition function. Let's find a relation between Helmholtz partition function and Helmholtz free energy. Relation between partition function and Helmholtz free energy. Is it alright? Okay. So Helmholtz free energy, I will denote it as A. So A is equal to what? Minus KT LNZ. Okay. Where see Q, okay, Z. Z1, I will write Z1 as single particle and Z2 as n particle. Hmm. So A is equal to minus KT LNZ. Hmm. Next, let's write difference between microcanonical and canonical ensemble. What is the difference between them and why we prefer canonical ensemble? See, microcanonical here. What are the macro states? Macro states are N, V, E. In canonical ensemble, what are the macro states? Macro states are N, V, T. Alright. So here, your N is constant, V is constant, E is constant. Okay. And here, what are constants? The thing in the bracket, N is constant, V is constant, and your T is constant. Is it alright? Yeah. So, but in microcanonical ensemble, if you see, this is the here E is constant as I've told, energy is constant, so there is no exchange with the other there is no exchange with surrounding. But here what happens there is energy is not constant here. Okay. What is constant? T is constant. In temperature is constant, but energy is not constant. Okay. So in microcanonical ensemble, internal energy U E is constant for each system of ensemble. Okay. And actually, this maintaining this E as constant is a very tedious task, very hard task from practical perspective. And also monitoring to E as constant is very difficult. Okay, and on the but on the other hand, if you see in canonical ensemble, it's very easy to maintain temperature as constant. We can do that, but maintaining energy constant is a very hard task. But maintaining temperature constant is not that hard. It's very easy. And for that, we have to put all the system in contact with the heat reservoir. This is the heat reservoir. Okay, heat reservoir of infinite heat capacity. Okay, it can take as much heat as we can give it, and that's a very easy task. Plus, monitoring of maintaining temperature T is constant is also easy because for that we just have to put thermometer in each system. Okay, because we if we have to monitor the temperature, whereas monitoring E as constant is not that easy. Okay, yeah. Okay, you can we can add a question here. Like you can be asked in the interview. This question you can be asked why if we can study Question can be if we can study any system, via micro-canonical micro-canonical ensemble hmm, approach, micro-canonical ensemble approach, then why, then why we need canonical ensemble? Then why we need canonical ensemble? Then why we need canonical ensemble? This is the question. If we can study any system via micro-canonical ensemble, then why we need canonical ensemble? As I told you just now, you can write, you can say in an interview like in micro-canonical ensemble, what happens in micro-canonical ensemble? Maintaining E, maintaining E as constant and monitoring of it, monitoring of it is a very tedious task. Is a very tedious task from practical perspective. From practical perspective. Okay, that's why we are moving away from micro-canonical ensemble. Okay, and also in micro-canonical ensemble, we have to find we have to find number of microstates, number of microstates, uh, and for some system it's impossible, it's almost impossible, it's almost impossible to find number of microstates. Okay, so that's the reason we can study a system by a micro approach, and we need what canonical instance. Okay, yeah. That's the reason for it. Mhm. Okay, we wrote a partition function here. Okay, there is a partition function. Okay, for example, this was your what? Okay, now we'll write quantum mechanical partition function. Quantum mechanical partition function. What is that? So for single particle, the partition function is for a single particle. Partition function is Z1 is equal to summation r gr e to the power minus beta er. Okay, hmm. Where gr is what degeneracy of er level. This is for a single particle. For n number of particles, a system for a system of n particles, for a system of n particles, distinguishable particles. So Zn is equal to Z1 into Z2 into Z3 into what? Zn, like Zn times, right? N times. Hmm. So I can write Zn is equal to, this is actually Z1, all are Z1 only, same partition motion for everything. So Z1 to the power n. Okay. Now what are the indistinguishable particles? Indistinguishable is Zn is equal to Z1 to the power n, but I have to divide n factorial here. Okay, I have to divide n factorial here for indistinguishable particles. All right. Now, this was a quantum mechanical partition function. Now, classical mechanical partition function. Classical mechanical. Okay. So, what is it? For a single particle? For a single particle, what is it? Z1 is equal to 1 by h to the power f, where f is a dimension. Q, P. Here both the position space and momentum space will be there included. Minus beta h. H is a Hamiltonian. df. Q means a dimension. Okay. dfp. F is a dimension. Right. Or degree of freedom. It's a degree of freedom. Now your h is a Hamiltonian. That means the total energy of the particle. Right. So if you see, if I give you some limits, what will be the limits of the integrations? So for a 3D, we will be using spherical coordinate system in this integration. Okay, spherical coordinate system. Spherical coordinate system. The limit will be 0 to infinity. Hmm. In 2D, it will be polar coordinate system. Again, here also it is 0 to infinity. And but in 1D, this is Cartesian coordinate system, and it will be over all space. That means it will be what? Minus infinity to plus infinity. Okay, that's the thing. So yeah. For n particle system, this is for single particle system I wrote. For n particle system, it will be for n particle system. First is a distinguishable. That is Zn is equal to Z1 to the power n. That means what? Whole of right, 1 raised to the power f. But this one will be what? Product. This is a product. Okay. I is equal to 1 to n. Summation to the power minus beta ei b f q. Okay. So this indistinguishable n will be divided. It won't be the exponent. It will be divided indistinct. Z is equal to Z1 by n. Is that alright? So Z1 to the power n by n factorial. No, sorry. My bad. I'm sorry. Okay. Okay. So how will we decide? I just wrote classical mechanical partition function, quantum mechanical, but how I'm going to decide whether the system that is given is we have to use a quantum mechanical distribution of partition function or classical mechanical. Okay. So write a question here. You can begin an interview question. How will you decide or identify? How will you identify? How will you identify whether the system is whether the given system okay, whether the given system is classical mechanical or quantum mechanical. Whether the system is classical mechanical or quantum mechanical. How will you decide? Okay. The thing is, don't see the words as distinguishable, indistinguishable because both are there in classical and quantum mechanical. How will you decide? We have to decide it by looking at the energy eigenvalue. Okay, by looking at the energy or analyzing the energy eigenvalue for the system. Energy eigenvalue for the system. Okay. So we know if it is the energy values are quantized or discrete, it is quantum mechanical approach we have to find. So if energy eigenvalues, what if they are discrete or quantized, hmm, discrete or quantized, then we know quantum mechanical approach we have to find for partition function. If they are continuous, this is classical mechanics. Okay, if it continuous, if the energy is continuous, then classical mechanics. Okay, is it all right? Okay, yeah. Now we will calculate partition function for various systems. Okay, in write down various systems in canonical ensemble right now. Various systems in canonical ensemble. Okay, first system diagram, classical ideal gas. First system is what? Classical ideal gas. Okay, so here we will consider a classical ideal gas containing n particles, okay, that are non-interacting, okay, like monoatomic, non-relativistic, and indistinguishable particles. And there is a container of volume V. In this container of volume V, there are n number of particles. Okay, n number of classical ideal gas particles like containing n particles that are non-interacting. These are what? Okay, n particles in a volume V. These particles are what? What? Non-interacting, non-interacting, monoatomic, monoatomic, non-relativistic, non-relativistic, and indistinguishable. And indistinguishable. Okay. So these are some of the like the particles are this way. Okay. So this is a what? Classical ideal gas. Okay. Ideal means what? What? Ideal is, yeah, ideal, that is non-interacting. And what do you mean by non-interacting? Non-interacting means actually the potential energy there is zero. Okay, that's the meaning of non-interacting. And classical means what? Classical, sorry, energy for a single particle here will be what? Classical ideal, right? So energy is potential energy plus, sorry, kinetic energy, potential energy is zero. So kinetic energy is left, that is p square by 2m plus 0. That is p square by 2m. And this is also what? Non-relativistic. Okay, so your energy is what? P square by 2m. Is it alright? Okay. Okay. Now monoatomic is also there. The particle is also monoatomic. Monoatomic means what? Degree of freedom we know. F. Degree of freedom is 2 and 2. Okay. Degree of freedom is what? D into n minus k. D is dimension, n is number of particles, and minus k. Sorry, number of constituent. Yeah, number of constituent particles. minus k. Number of, that means k is your constraint or number of relations between particles. Is it alright? Okay. So now, see, D is the what? Space in which particle is moving. These are your dimension. Alright. D is your dimension. Okay. Now, uh, so these are also indistinguishable. Lastly, indistinguishable. So we write indistinguishable. So if it is indistinguishable, how do we calculate the partition function? We divide it by n factorial if you remember. Z1 to the power n by n factorial, right? Partition function. So let's write it Zn is equal to Z1 to the power n divided by n factorial. Okay. Uh, so we have to find the Q1, this Z1 first, isn't it? Z1 first. We know energy we did it is P square by 2m. Okay. And if you see, this is actually not quantized, this is continuous energy. E square by 2 means continuous energy. So, which kind of approach will be used here? Continuous means classical mechanics approach. Okay, classical CM approach will be used to calculate what? First, we have to decide which approach will be used to calculate the system. For that, we have to see what is the energy, whether it is continuous or discrete. So, CM approach. So, what is CM approach? You see yourself, what is CM approach? This is a CM approach, right? For indistinguishable particles. Okay. But what is Zn? This is Z1. Okay. Okay. So let's calculate this. This is your Z1, isn't it? So just put the value Z1. So first we have to calculate Z1 because this is the whole thing. So Z1 will be 1 by h to the power f e to the minus beta h dfp dfq. Is it right? Yeah. So here these are what 3D ideal gas. This is 3D. So 1 by h cube integration e to the power minus beta. What is the Hamiltonian energy? Energy Hamiltonian is p square by 2m. So beta p square by 2m. Then your this is q. Is it all right? Hmm. Because f is a 3. I should say. Okay. So now tell me how to do it from here. See, this is in p, right? This is in p space. So I can separate them a bit by hq like this. Is it all right? Okay. And this is now your spherical. This is 3D system. For 3D, we will do what? We will use spherical coordinates. If you have seen before, we have written. What is it? So yeah, for 3D, we'll use what? Spherical coordinate system. We're going very step by step. Okay, please understand. Hmm. Spherical coordinate system. So let's write it. Spherical coordinate for which space? For this one. And this one d. Okay, this is your exactly what? This is if you see. This is exactly what? Hmm? dq. Okay, dqq. This is your e to the power minus beta p square by 2m. Okay, I can write it as 4 pi p square dp, isn't it? Because we are using spherical coordinates. Hmm. And this is why I can write it here. For okay, this is a word exactly volume, isn't it? This is a volume. So v by h cube and 4 pi comes out integration minus beta p square by 2m. And let me write the p square here dp. Okay, and if you see in spherical coordinate, what is the limit? 0 to infinity. We have written. We're going very step by step. Please remember 0 to infinity, isn't it? So let's give the this one as 0 to infinity. So if you remember 0 to infinity x to the power m, e to the power minus alpha x to the power n dx. The integration is 1 by n gamma of m plus 1 by n alpha m plus 1 by n, isn't it? So here, if you see, this is 4 pi v by hq, integration 0. Okay, your m is 2, n is also 2, so okay, no problem. 1 by 2 gamma 2 plus 1 by 3, that is 3 by 2, and alpha is a what? Beta by 2m, beta by 2m, 3 by 2. This is all right. Gamma 3 by 2 is how much? Half gamma half. Gamma half is root pi, so this is root pi by 2. So 4 pi v by hq into 1 by 2 root pi by 2, and this is your, it will go up, it will become 2m pi beta to the power 3 by 2. Is it all right? Is it all right? Mhm. So this is 4 pi to the power 3 by 2. Okay. 4v pi to the power 3 by 2 by v hq. Okay, and this is also 4 na? This is 4. 2m by beta to the power 3 by 2. Okay, can I write hq as h square to the power 3 by 2? Isn't it simple to cancel hq? So I will write it here. 4 4 cancel, v into pi to the power 3 by 2. hq is h square 3 by 2, 2m by beta to the power 3 by 2. So all the 3 by 2's I will make one bracket. So 2m pi beta h square by 3 by 2. Now tell me what is beta. Beta is a 1 by kbt, right? So I will put it there. So v into 2m pi 1 by kbt h square 3 by 2. Now kbt goes up 2m, so m 2 pi m kbt by h square to the power 3 by 2. Okay, and this is your z, isn't it? This is your z1 only. We have only calculated z1. Okay, so your partition function is what? Z1 to the power n divided by n factorial. So let's put it, this z1 to the power n, that is 2 pi m 2 pi m kbt by h square to the power 3 by 2 n. N is be there, n will be there, divided by n factorial. Right? Isn't it correct? Yeah? Yeah. So this is your partition function. Is it alright? From here you can calculate your u minus del by del beta of ln z, then a minus kt ln z. Okay. A is a what? And moles free energy. Okay. Entropy can also be calculated if you calculate moles free energy. Entropy x is equal to minus del A by del T n V are constant. And pressure will be P is equal to minus del A by del V n T are constant. Okay. In entropy, n V are constant, T is the variable. In pressure, n T are constant, V is the variable. Then next heading is level systems. Level systems. So here we'll be given some energy levels and the respective degeneracies. Some energy levels, then the degeneracies, okay. And we have to fill up some particles in these levels. Like these levels will be given. We'll be given some particles, and you have to fill up these particles and according to the degeneracy. Okay. So this is known as your level system. Okay. So if you are given to like it is an incomplete word level. It can be two level or three level like that. If you are given two levels, then two level system. If you are given three level, then three level system. Right. So here particles can be given as classical particles, or particles can be classical particles or quantum particles, which are, what are the quantum particles? Quantum particles can be bosons or fermions. Okay, they can be bosons or fermions. This is all. Okay. So we have to fill those bosons and fermions, and after that, after arranging, we have to find what? We have to find partition function z. We have to find u from partition function, moles free energy, pressure, entropy, okay, probability, whatever you are asked, you have to find out. Okay, yeah. So, alright. So now, mm, how to approach these questions? So just give a heading: approach for fermions and bosons. Approach for fermions and bosons. Okay. So how it will be given in the question? Somewhere spins won't be mentioned, and somewhere spin will be mentioned directly or indirectly. Okay. For both cases, working procedure is different, and that's why we have classified our discussion in two ways. Like we have to fill, for example, three fermions. Okay. It will be given like this: fermions, three fermions, and here spin won't be mentioned. Spin not mentioned. Okay. Then four bosons. It will be given like this: four bosons. Spin not mentioned. I'm just giving you some examples. Okay. I'm not telling you to do anything. Just examples, like how it will be given in the question. Then it will be given four particles following, it can be given this way: four particles following Fermi-Dirac statistics. So you tell me which particle it will be. Fermi, that means obviously it will be, these particles will be what? Fermions, isn't it? This is given indirectly, fermions. Then three particles, another way it can be asked: three particles following Bose-Einstein statistics. Bose-Einstein statistics, right? So here Bose means particles will be bosons. Okay. Then again they can be asked. They can ask you four electrons are there. Four electrons. Electrons are what? Fermions. Yeah. It will be not given. Only four electrons will be written. So spin mentioned indirectly. Yeah. Indirectly spin is mentioned. So for electron spin is what? Half. Okay. You got it. Then again the same way, three photons. Okay, photons are what? Photons are bosons. So again, spin is indirectly mentioned, that is spin is 1. Okay, spin is 1 for photons. Yeah, these are bosons. That's why integral spin. This is odd integral spin. This is like half odd rational spin. You can say also. Okay. Otherwise, directly mention 3 spin half particles like that. 3 spin 3 by 2 particles. So, so these are the ways question can be asked in you. Asked to you. Okay. Next is the what? So, okay. For example, spin is not mentioned. So how to do it? Spin not mentioned. So for fermions, let's see for fermions how will you solve it. So step one will be what? Find out number of diagrams or ways how we can arrange them. Diagrams or ways. Okay. Number of diagrams would be what? It should be number of ways for fermions. It is GICNI. Okay, GICNI. All right. Step two. What is step two? Step two is like fill up the particles considering them as what? Okay. Fill up the particles consider them as indistinguishable. Okay. Fill up the particles considering them indistinguishable. Fermions are indistinguishable. In because that means we won't be able to give them names like ABCD. Right? If spin is not mentioned. Alright. Now that means what do you have to do exactly? Fill up only one particle in each state, in each energy. Only one particle in each level. Okay, in one particle in each level. Right? Now calculate total energy from the diagrams in each diagram. Calculate total energy in each diagram. Now also you can next step is make a table for possible total energy values for possible total energy values and also write their respective degeneracies. Also write their respective degeneracies. Is it alright? Okay. Now finally write down the partition function. Z is equal to summation I g I a to the power minus eta. Okay. Is it alright? Now for bosons. This is for fermion. What will you do for bosons? For bosons, how will you solve it? See for bosons, again find a number of ways you have to find out. Okay, how to do that? Number of ways is Ni plus Gi minus 1. This is for bosons. Factorial divided by Ni factorial Gi minus 1 factorial. Okay. Now fill up particles like you can any number of particles you can fill. So fill up the energies levels. Fill up the energy levels. There are no restrictions. No restriction. Okay. There is no restriction. Number three is calculate total energy. Calculate total energy in the system, each system. Number four is write down the partition function. Is that okay? So that's the one. So here another important point is See, language of the question will contain the term indistinguishable, but do not divide it. Just that indistinguishable is written, don't divide the partition function with n. Okay, don't do it. It's wrong here. Okay, in this case, it's wrong. Alright? Mm. Okay, now write a question. We'll solve the question, you will understand. This is three energy levels are there, plus 2 epsilon, plus epsilon, minus 2 epsilon. Okay. G is 1 here, G is 1 here, G is 2 here. So you have to arrange two bosons in these levels. Okay, two bosons in these levels, and for that you have to calculate partition function. Okay, probability of the energy being 2 epsilon. Okay, and then your internal energy and Helmholtz free energy. Is it all right? Okay, so this is plus 2 epsilon, epsilon minus epsilon, minus 2 epsilon. This is G1, G1, G is equal to 2. Alright, so two bosons. So number of ways of arranging bosons is what? Number of ways of arranging bosons. We know the formula Ni plus Gi minus 1 factorial divided by Ni factorial Gi minus 1 factorial. So number of particles are how many bosons? Two bosons we have to do. Two bosons and three energy levels. So 2 plus okay. What is the total degeneracy here? Total degeneracy is how much? 10. Sorry, 4. 1, 1, 2, 4. So 4 minus 1 factorial divided by 2 factorial 4 minus 1. 6 minus 5 factorial divided by 2 factorial into 3 factorial. 5 factorial cancel with 5 into 4 divided by 2, that is 10. So answer is 10. Number of ways is 10. Okay. So 10 number of ways to arrange these particles. Alright. So let's do it. So this is your sorry. Okay, because the energy degeneracy is 2 here. So I can arrange two particles here only plus 4 epsilon. Okay. Now I can do this. Bosons means no restrictions here and here. Now I can also do this here, here. So this is a word minus epsilon. I'm doing it fast. I know you can understand. Here, here. So this is minus 2. This is 0. Here, here. This is also 0. Now here and here. This is 3 epsilon. Here and here. This is also 3 epsilon. Now only one is left arrangement. This is 4 epsilon. Okay, so there are how many ways? If you see, there are 10 ways. We could do it 10 ways. So we just have to write the partition function this for this 10 ways. That will be z is equal to summation I gi e to the power minus beta ei. Alright. So again, see degeneracy everything. Okay, plus 4 epsilon. Okay, let's write it for everything. 1 into e to the power minus beta into 4 epsilon. Okay. Sorry. Okay, this is minus 4 epsilon. And minus 4 epsilon is only once here. That means degeneracy 1. So 1. 1. Plus. Now. Sorry, this is minus. Plus. This is 2 epsilon. 2 epsilon is also only once. So 1 into e to the power minus beta. Plus. Now this is 4 epsilon is coming 3 times. Okay. So 3 into e to the power minus beta 4 epsilon. Okay. Now minus epsilon is coming once, so plus 1 into e to the power minus beta minus epsilon. Okay. Now your 3 epsilon is coming twice, so 2 into e to the power minus beta 3 epsilon. And your 0 is coming twice also, so 2 into e to the power minus beta 0. Okay. So these are the energies. This is your partition function. Okay. Probability of getting 2 epsilon. So probability of getting 2 epsilon will be what? GR e to the minus beta ER divided by summation GR e to the minus beta. So this one only for 2 epsilon we have to do. For 2 epsilon, if you see what is the term, this one only, right? So 1 into e to the power minus beta 2 epsilon divided by the total partition function we have to have. Okay. Is it all right? Now we can calculate the potential energy, that is minus del by del beta of ln z. Okay. So whatever z you got, you just put it here. See, this is a very just for calculation, like practice question, so we don't need to do everything. Okay. And what is the Helmholtz free energy? Minus kT ln z. Okay. So these are some of the ways to do it. Okay. So this is for boson. I did for boson. So I am giving you homework to do for fermions. Okay. This is the homework. You have to solve it. For fermions, there are two fermions. Okay. There are two fermions. There are two energy levels, 0 and epsilon naught. There are two fermions. This is G is equal to 1, G is equal to 2. And you have to arrange them in these two levels, and you have to calculate the partition function. You have to just calculate the partition function for this one and entropy. Okay, partition function and entropy. Okay, so yeah, so these are some we have done this till this much. We'll be solving more questions from here so that your concepts will be clear from this chapter. It's a very interesting chapter. Okay, yeah, that'll be it for this class. Okay, and thank you very much for watching. Yeah, keep tuned to the channel. Thank you very much.